So I'm Zach Swiecki, and I'll be presenting on iSENS, which is an integrated approach to combining epistemic network analysis and social network analysis. So as many of us know, the complex problems we face in domains like engineering and the military, and in particular medicine as we're seeing now, these often require the coordinated effort of multiple individuals to solve. And so because of this, collaboration has been widely recognized as a critical 21st century skill. And there's been a significant amount of research that has gone into assessments of collaboration. Some relatively recent examples are the PISA 2015 assessment and the Assessment and Teaching of 21st Century Skills project. But one particularly promising method for assessing collaboration is collaboration analytics, or more generally the application of learning analytic techniques to some collaborative situations. So some techniques that have been used include things like clustering and lag sequential analysis and social network analysis, to just name a few. And techniques like these are potentially transformative because they allow us to look at collaborative processes, not just outcomes. They can be applied in some authentic environments, authentic collaborative environments. And in some cases, they can be applied in real time. But for collaboration analytics to work, we of course need some way of modeling collaboration. In order to model collaboration, we need some way of representing the salient aspects of collaboration. And so research in the learning sciences has suggested what some of these salient aspects might be. So for example, work by Vygotsky on the zone of proximal development, work by Hutchins on distributed cognition, and Rochelle on joint problem spaces has established that collaboration has at least two really important dimensions. There's a cognitive dimension, which typically involves things like representing, investigating, and making attempts at solutions to problems. And at the same time, there's the social dimension, which involves things like sharing information, negotiating meaning, and maintaining and repairing a shared understanding of the problem. And there have been several learning analytic techniques that have been used to investigate both the social and cognitive dimensions of collaboration. The ones I'm going to focus on today are network analyses. And with respect to the cognitive dimension of collaboration, network analyses are powerful tools that align with theories of cognitions that suggest that it's not just the presence of isolated bits of knowledge that matter for complex thinking, but instead it's the ways in which these pieces of knowledge are interrelated or connected to one another. So one technique that has been successfully used to measure these kinds of connections in a variety of domains is epistemic network analysis. With respect to the social dimension, network analyses generally align with theory on collaboration that suggests that people are not just isolated actors in collaborative situations or in many collaborative situations, but instead they interact with one another to form patterns of social connections between individuals. And so one technique that's been used successfully to measure these kinds of connections in a variety of domains is social network analysis. And so here we have two network techniques that are quite powerful, but there have been relatively few attempts to combine them to study both dimensions of collaboration at the same time. So one notable exception to that is work by Gosevich and colleagues on the social-epistemic network signature. And so that was used to combine social and epistemic networks to investigate collaboration in an online setting. So prior work using this technique found that ENA can predict differences in social structure, and that SNA can predict differences in discourse content or the epistemic content. So there's this interrelationship between the cognitive and the social. And also that SENS, which combines the two techniques, can predict student outcomes better than either method alone. So this is a really important step forward for looking at both of these dimensions of collaboration at the same time. But there were a few limitations that the current work is trying to address. So first, prior work on SENS was applied in an online setting in which students were discussing on forums. Whereas here we're looking at a team setting where teams, particularly ones that have been trained together and are working together on same problems over time, tend to be more interdependent and more interactive. So it's worth looking at this, this approach in a setting like that as well. The second thing is that the previous analysis treated ENA and SNA metrics as independent predictors of student outcomes. But theoretically, and according to some of their results actually, we might have reason to think that these dimensions or these metrics are interrelated. And finally, the previous work didn't develop a combined representation of the epistemic and social networks that could be used to look at both dimensions simultaneously. So to address these limitations, we developed what we're calling the Integrated Social Epistemic Network Signature, or iSENS. And so this combines ENA and SNA metrics into a unified metric and also a unified visual representation for investigating collaboration. So to test this, we're using data from a team setting and asking the following research questions. We're looking at what patterns of cognitive and social connections are salient for these teams. What do ENA, SNA, and iSENS networks reveal about these teams? And does iSENS predict team outcomes better than ENA alone, SNA alone, or the SENS approach, which splits out ENA and SNA into independent predictors? So to test this, what we did is we used data from air defense warfare teams and training simulations. So these teams participated in training scenarios that simulated working on warships, and during these simulations they used radar to detect aircraft or other vessels in the vicinity and decide whether they were friendly or hostile and whether they should be engaged in combat. And so in this context, these aircraft or other vessels were called tracks. You'll see that come up a number of times. And in the data, each team consisted of up to 6 individuals. So there were 2 command roles on the team who were primarily responsible for giving orders and making tactical decisions. And there were 4 supporting roles on the team who were mostly responsible for passing tactical information to the commanders. There were also some people external to the teams that communicated important scenario information that were also included in the analysis, so you'll see those come up later. But in total, the data set had 16 teams, and they participated in the same 4 training scenarios for a total of 64 team scenario combinations, which are going to be our unit of analysis for most of the study. So for each of these team scenarios, the data consisted of a team scenario performance score on a scale from 0 to 55 that looked at different aspects of teamwork behavior, and also a transcript of their communications. So to look at our first research question, we conducted a qualitative analysis on the transcript data using discourse codes developed in a prior study of this same data. So these codes are capturing salient concepts in the team decision-making process, such as seeking information about what's going on, passing information about tracks or the identification of tracks or their behavior, and also giving things like orders to warn or engage in combat with tracks. And to code the data, we developed keyword-based classifiers for each of these codes. And we achieved a 3-way validation between 2 human raters and the automated classification system using both Cohen's kappa and Schaefer's rho. So for our second research question, we wanted to develop ENA, SNA, and iSENS network models using the coded transcript data. So for the ENA analysis, what we did is we developed networks for each individual in the data. And to do that, ENA identifies the lines associated with that individual or given individual, and it moves a window over the data to identify the connections or the co-occurrence between the codes in the last line of the window and the codes in the prior lines, regardless of whether those prior lines are contributed by that individual or if they were contributed by other members of the team. So in this way, ENA is accounting for interdependence that exists between a given individual and their teammates, so how they're responding to what's going on in the common ground of the problem solving. So moving this window and counting connections in this way, ENA creates network models for each individual that show connections that they made in their discourse in terms of the codes that are in the discourse. And as the window moves over the data, these connections are going to get stronger, and as they occur more frequently, and new connections are going to arise by the end of the team scenario or the data set. And ENA can create similar networks for different individuals in the data, as well as summary points that correspond closely to the center of mass of the network. So here, the more connections you have to the left and higher up in the space mean that the summary point will be further to the left and higher up. And more connections to the right and lower down move the summary point to the right and lower down. So what this means is that we can actually compare the connections individuals made visually without looking at their whole network diagrams. We can use their positions in the space. And this is useful because it allows us to compare many networks at once, more than 2. And using ENA, we can calculate the centroid of groups of points, either for particular teams in the data or larger groups that you might have in your data. So this is their mean position in the space. And for each centroid, ENA also creates a mean network or an average network for the group. And if we want to compare the networks of different groups, what we can do is we can calculate a network subtraction that shows the connections that are stronger in one group relative to the other. So finally, using the placement of these network nodes in the metric space, we can interpret what the dimensions of the space mean. So in this example, the connections on the left have to do with actually doing something with information about tracks, so track processing. On the right, we have things like basic information about detection and track behavior, those connections. So we can say that this first dimension distinguishes individuals in terms of those who focus on track processing versus track information. We can do something similar for the next dimension, and we see that connections at the top of the space are mostly to seeking information about aspects of the situation, while connections at the bottom have to do with kinds of tactical actions like giving orders or recommendations in response to information. So the second dimension is going to be distinguishing individuals in terms of those who seek a lot of information versus those who act on information with orders and things like that. So to take a step back and talk about how these models are actually calculated, what first happens is ENA calculates the summary statistic for each network. And it does that using an adjacency matrix that indicates the number of times a given pair of codes were both present in the window. So then ENA is going to perform a dimensional reduction on the set of all the adjacency matrices we have for everybody in the data set. And that's going to produce the summary points that I was showing you, what we call ENA scores. And also a set of new dimensions that are going to maximize the difference between these ENA scores. So this is a process similar to what principal components analysis and other dimensional reduction techniques do. And one way to interpret these dimensions is using the loadings from the dimensional reduction, and these show how associated each connection or variable is with the dimensions. But ENA uses a little bit of a different approach. So we actually use an optimization routine to position the network nodes in the space such that they correspond with those loading vectors. And what this allows us to do is view the networks and the ENA scores in the same space. So that's a lot about ENA. We're going to move on to the social network analysis quickly here. So for the social network analysis, we adopted a similar approach where we moved a window over the data. But this time we were looking for connections between speakers, not between discourse codes. So using these connections, SNA makes a network model for each individual in a given team scenario. And as this window moves over the data, we can see those connections get stronger and accumulate to form the final network for that individual. And we can create similar networks for other individuals on the team scenario and average those networks to get a representation of the overall patterns of social interaction for the whole team. For the iSENS analysis, what we do is we use ENA to position the individuals on each team scenario in the epistemic space defined by the connections they made. So these are the actual ENA scores for those different individuals on the team. And then what we do is we overlay the social network, their team social network in that space. So we can see both what they talked about in terms of their position and also how they were interacting with each other and where the connections are most dense, for example. So moving on to the third research question, what we wanted to do is see which of these models was better. So what we did is we developed an ENA model, a predictive ENA model, SNA model, an iSENS model for each team scenario in the data set. And we used these to predict team scenario outcomes and then compared the models. And these were created using hierarchical linear modeling. So these models predicted that team scenario performance score that I mentioned earlier. For the first model, the ENA-based predictor that we used was the team scenario centroid, or each team scenario centroid, so the mean position of the individuals on that team in the epistemic space. For the social network metric, we use the weighted network density of each team scenario. So this is the sum of the connection weights in the network divided by the number of possible connections in the network. For the iSENS model, we used what we're calling the iSENS centroid. So this is the mean position of the individual points in the epistemic space, but weighted by their social network connections. So this centroid will tend to move closer to where the social connections are most dense in the network. So each HLM also included the team variable as a random effect. So this is the hierarchical nature. The team scenarios are nested into different teams, so we want to account for that relationship. And so the main difference between all these models we're testing is in terms of their predictors. And to be really clear, this is probably the most important comparison here. It's including the SENS model, which is separating out the ENA predictor and the SNA predictor as independent variables. And then we're comparing that to the iSENS model, which is using that unified metric. To compare these, we actually look for the presence of significant predictors, and for those models that included significant predictors, we compared their performance statistically by taking bootstrap samples of the data, making the HLM models for each of those samples, calculating the error of the model prediction on the samples, and then comparing the distributions of those errors for the different modeling approaches using confidence intervals. Okay, So for the results, for our first research question where we looked at the qualitative patterns of cognitive and social connections, we found that, and here I'm summarizing some work that results that were aligned with previous qualitative studies on this data, but importantly we found that low-performing team scenarios focused their social interactions on seeking information to understand what was going on in the tactical situation. And high-performing team scenarios focused their social interactions on acting on the tactical situation with things like orders. So for our second research question, where we look at the actual different network models for this data, we'll first start with the ENA model, and this is the overall ENA model for the high performers in green and the low performers in red. These are their mean networks and the subtraction between them. And so we can see that this model is corroborating what we found with the qualitative analysis. So in particular, low performing team scenarios were characterized by strong connections between seeking information, detection, track behavior, and assessment. Whereas the high-performing team scenarios, were characterized by connections between these tactical actions like orders in response to information. So focusing in on one team will help show the value of the SNA and iSENS approaches. So here's one high-performing team scenario. The points there are the individuals on the team, and the square is their centroid. And here we can see that most of the individuals on the team are focused on talking about track processing and tactical actions, as we can infer from their location in the space. But one member of the team, this is the EWS, a supporting role, is focused more on seeking information and track information. So looking at the social network for this team, we see that most of the dense connections are between the TAO and the CO, who are commanders, and then the TIC and the IDS and this other category, which are supporting members. So for the iSENS network, where we overlay this social network into that epistemic space, we can see these social connections in relation to what the individuals talked about. So here we can see that the EWS made cognitive connections that were very different from the rest of the team, indicated by the position, right? And their position actually has the effect of putting the original ENA centroid, pulling it closer to them, higher up and to the right. But as we can see from the social connections here, the most dense interactions are between the rest of the team, really. So when we plot the iSENS centroid, we see that centroid is weighted or pulled closer to the lower, and to the left, closer to the dense interaction of the team. And so that's the effect of the iSENS approach. So what the statistical tests that we look at in the next research question do are testing whether effects like this are better for predicting team scenario performance. So that's what we did when we compared the predicted models in our third research question. And here are the results of those HLM models. For these results, we can see that only the SENS and the iSENS model had significant predictors. So in both cases, this was the position of the centroid on the second dimension of the ENA space. So the more team scenarios focused on seeking information, turns out the worse they performed. So these models are actually very similar in their interpretation, but we want to see which of these perform the best. So to do that, we can look at the bootstrap error results. So these results show that on average, the iSENS model had the lower errors. It's the left in the parentheses. And the confidence interval around the difference in those doesn't contain 0. So this suggests that the iSENS model, which integrated the ENA and SNA metrics into one metric, performed better in a predictive model. So this work suggests that iSENS is a better approach to modeling the social and cognitive aspects of collaboration, at least in this context. And of course, there are some limitations that we will want to discuss. One is the most obvious one, that the results are based on one context, and they don't show that the iSENS approach is going to be better in all cases. We would need to test this on a variety of different collaborative scenarios to see whether the results aligned with what we have here. And second, the models that we use in this study didn't explicitly represent the order of the social or cognitive connections, so we're using undirected graphs. So that order could be important. But however, some previous analysis that we've done on this data suggests that unordered models actually outperform sequential models, but we expect that this might be different for different data sets. So future work will test this approach for other data sets in which we think the actual order of the interactions is important. And I do want to highlight that the order is taken into account by the fact that the moving window is used on the data, but there's no distinction between the direction of the connections. And finally, the last limitation I want to discuss is that we used here a relatively simple SNA metric as a proof of concept. So there are other techniques that we might combine with ENA in the future. I think Bodong mentioned some ones that I think would be really cool to try out with REM. Also, it would be useful to look at some individual level SNA metrics and combine those with the individual level ENA scores rather than the team level, which we were doing here. So things like betweenness and centrality. The reason why we didn't do that here is because our outcome level was at the team scenario level. But despite these limitations, the work here presents a unified metric and a unified representation for the cognitive and social dimension of collaboration. And that can be used to capture information about both of these dimensions simultaneously and hopefully giving a more complete understanding of collaboration. So we expect that this will be a beneficial tool for researchers who wish to study the relationship between these two phenomena. And our hope is to eventually integrate this technique into collaboration analytics dashboards to give teams and educators some on-demand information about their social and cognitive activity. Okay, so I think now we have some time for questions. Yep.